In this video, we will try to get the value of delta IL, delta VC in case of continuous conduction mode. Let us draw the diagram. So this is what the expression we have, diagrams we have. So we can get is a freewheeling diode and the inductor and capacitor. The voltage across the capacitor is VC, and which is equal to V0. So here we are trying to get the output current as DC as possible, and what we can write here is we can apply the KVL and voltage. Let us say the voltage across this is V0I. So if we apply the KVL, we can also get VL, voltage across the inductor. So assuming, since it's a continuous conduction mode, during the turn on time the inductor will store the energy. During the off time the inductor will discharge the energy. So design should be such that during the one cycle the energy stored and energy released must be equal. Otherwise it will keep on storing the energy and you will not get a proper output. So if the net energy in the inductor is equals to 0, we can write VL is equal to, we can write L di by dt. This is the formula, voltage across the inductor. So we can rewrite this. So this is one equation. We can write what VL is nothing but Vd minus V0. VL is Vd minus V0, which is equals to L di by dt. Di is delta IL divided by dt is it is on for the duty cycle d times of ts. So we can get this relation on time. Also during the off time we can get the output voltage across this is V0 and this is VL and this is a closed circuit. So we can get VL is equal to minus of V0. So minus of V0, I am writing intensely, this is small letter, is equal to L del IL, because it is rising to a certain value, it is also falling, so del IL will be negative, divided by 1 minus d times of ts. So this negative get cancelled out. So from both the relation we can write del IL is equals to dTs multiplied by this Vd minus V0 by L is equals to 1 minus dTs V0 by L. So this implies these two are equal. So let us equalize this. dTs Vd minus dTs V0 is equal to Ts into V0 minus dTs into V0. So from this expression we can find that this two cancels out. So what is ultimately we are getting here is dTs Vd is equal to Ts V0, or which is giving a very simple equation, V0 is equal to d times of Vd. So this is the expression we are getting, d times of Vd is the V0. Now we can get the value of V0 is equal to d times of Vd. Also we can write here del IL is equal to d and d times of Ts, Vd as d times of V0 minus V0 by L. So here we can write as, this is okay, small letter now. This is not the right expression. Here it is Vd minus V0 is d times of Vd. So I can get the value of like d 1 minus d times Vd ds by L. This is what we're going to get. Del IL is equal to this much. Now, this is one equation, very important equation, del IL value. So this is also expression when Vd is constant, right? Vd is the input voltage, and usually this is constant because that is how it is, capital Vd is written here. So we can also get the maxima value. Maxima means we derivative with d del IL by d of capital D. This should be 0 at certain value of d. So if you substitute this, you will get a d derivative of with d and some all the constants. So this will be d into d minus d square. So this will be like 1 minus 2d is equal to 0, which implies d is equal to 1 by 2 or 0.5. So if we put the value of this, so I can get del IL max is equals to 1 by 2, 1 by 2. This is Vd ts by 4L. So this is one of the expression. We can keep it for any further use. Now this del IL we can also write as d 1 minus d Vd ts by, for ts we can take it bottom, L into Fs. We can also write like this, del IL. So it is inversely proportional to the switching frequency and directly proportional to duty cycle and directly proportional to the supply voltage. More the supply voltage, higher the value of del IL, and we can get a slope d, and we can create a slope over here that if we, let us say in the x-axis we have d duty cycle, and this side we have del IL. In that case, when the d is equal to 0, del IL is 0. When d is equal to 1, when both was 0 and 1, it is 0. And at d equals to 0.5, we know it is a higher value, peak. And rest we can make a slope out of it. So we can get a slope, and this peak value will be Vd ts by 4L. So this is the value of the peak, and we can get how the current ripple is going to vary with duty cycle. And with this scale like L, if the inductance is high, ripple is low, and if the switching frequency is high, then also ripple is low. So this is the information that we gather from del IL. Now we have to also evaluate del Vc. Let us do it. Now here the IC current, as it is from the other figure, that we know that IC will be following the IL, and for continuous current, so IC will be just starting from minus del IL by 2 to highest value will be del IL by 2. So it will be oscillating between that, and it is charging for the half of the cycle and discharging in other half of the cycle. So if average capacitor current is asked, what is the average capacitor current? We can write here as IC, capital C, IC is equals to, as this 1 by t, 0 to t by 2, because half the cycle it is, let us say this half is, it is on, and we can say IC dt, or we can also write, this is just a triangle, when we can write directly the answer as this value should be del I L by 4. So let us evaluate and try to see from this integration. So I'm integrating it like from this position to this position. So integrating like this is the slope of the height is del IL by 2 and this width, the base is TS by 4 in time, and this is 2 times this side and this side, so we can get in this way, or we can directly write average value is del IL by 4. So if we evaluate in this long process also, let us see what happens. So we can get here, these things cancel, and this will be 4 by TS, this is TS, all are TS, 4 by TS, and here, and this TS will come here again, this is square, and here you have del IL taken out. This T will be T square by 2. T square by 2, and this is limit from 0 to Ts by 4. So I can rewrite this as 4 del IL by Ts square. This is Ts square by 2 into 4 square. Here we missed one point. This is by Ts by 2 because we are taking from this value to this value and twice of this value. So here also this will be 8. So here this will be 8 again, and now these things get cancelled, Ts square get cancelled, and then you have got this is 2 left here, so this is del IL by 4. So this integration is actually from 0 to Ts by 4 if we take only this portion, Ts by 4, and it is taking twice, and this is the time when it is charging, so it is Ts by 2 times it is charging, and we are taking 2 times of it, like this half and this half. We can achieve this IC like this, or we can directly write the average capacitor current in this way. So once we get the value of average capacitor current, we can get the value of capacitor voltage. So we can write capacitor voltage Vc is equals to 1 by C integration of I dt plus Vc t equals to 0. So here del Vc is equals to obviously Vc minus the initial term. So this value is nothing but 1 by C integration of IC dt. So here we can substitute the value of here IC here, taking the capacitor is positive during the positive T by 2, the capacitor is charging. So that what is the average capacitor current is del IL by 4 into dt. So this gives us del IL by 4C. Here T is the limit, so T, a limit is 0 to T by 2, so T by Ts by 2. This is Ts all. So Ts by 2 we get here, so this is nothing but del IL by 8C, and this Ts will come here, this is Fs. So we can write here finally del Vc is equals to del IL divided by 8C Fs. So if I substitute the value of del IL from our equation, this is the del IL value, d 1 minus d Vd by L Fs. So d 1 minus d Vd by L Fs. This is 8C Fs. So we can write this as d 1 minus d Vd by 8 LC Fs square. So now what is, this is the one thing, and another is del IL that we have. Let us rewrite this d 1 minus d Vd by LFS. So we have the expression of del Vc and del IL. So like that we can now find out what is since we know the value of del VC and del IL, so we can decide that what should be the value of L and C, so that we can keep the del IL in certain range, or what is the value of a capacitor, so that del VC will be in certain range. So in that way we can design the value of here, we can design L first, then C and switching frequency, so that del VC and del IL will be in certain range, and we can control the output current and output voltage. Here we are trying to assume that current in the output is constant, and now we are trying to regulate the value of the del IL and del VC, so that we are getting appropriate value. So that we can think about the critical value of the inductance and critical value of the capacitance. So rest of the things we will get in another video.